So the first thing we'll look at is when this term is 0. So we'll look at just an airfoil, a two-dimensional airfoil. Okay, so the flow goes along the x direction, the z direction is the vertical direction, and you have a unswept wing that's infinitely long, right? That corresponds to the case where you have no variation in the y direction. So the derivative of pressure with respect to y is going to be 0. Okay, so let's look at what is the pressure field around the supersonic airfoil. So that is when you have 1 minus m squared, which is negative, times the second derivative of x plus only z is equal to 0. Okay, the first thing is just to enforce the idea that this term is negative, let's rewrite the equation into second derivative to x is equal to 1 over m squared minus 1, right? M squared minus 1 is positive, times the derivative of p to z. So think about what this equation is, and let's actually write an analogy to this equation. And you're going to see the analogous equation is just different variables. Let me just write not c, but a squared times d squared y dx squared. So has anybody seen this equation? Yes? In what scenario? In a PDE course, right? Okay. But yeah, let me. What kind of a physical phenomenon does this represent? A guitar string, right? That's actually exactly the equation that that describes vibration on the one-dimensional string, like a guitar string. So let's imagine this is a guitar string that's pulled tight by some force, right? So there is a force pulling the guitar string on both ends, and this guitar string has non-zero mass, which means it has inertia, right? So if the guitar string is actually bent like this, okay, now think about this string as a very soft string in the sense that it has no bending stiffness, but it actually would still vibrate because of the force you pull at the two ends. So if you think about this region, particularly if you think about this region, right? Intuitively, if you pull on both ends, how would this part of the string move? What would be the acceleration, right? Upwards, right? What is causing the upwards acceleration? The tension, the combined force from the two ends, right? You have tension that pulling along the string. The combined force would pull the string upward. And the angle of the combined force is proportional to the second derivative of this string, right? If you represent this string as a function of y with respect to x, then the second derivative is proportional, right, to how much combined force you get, and that combined force divided by the inertia, the density of the string, is going to give you the acceleration, which is the second derivative of the same function that describing the location of the string, right? So this equation is the vibration equation, and this equation is exactly the same except for different variables, right? Instead of a t, we have x. So it's a vibration in the as we move along in the x direction, right? We take different slices along the pressure field. Okay, that's analogous to time, and this x is now analogous to z. The location of the string is analogous to the pressure field. And this A here, which is the wave speed of this vibration is analogous to 1 over Mach number square minus 1. Okay? So let's actually write down some solutions, analytical solutions to this differential equation. There is actually very simple analytical solutions to, well, both differential equations, right? If you write, let's actually write down the analytical solution for this one first. It's actually pretty simple. Y is going to be a function of x and t, right? First solution is equal to f of x minus at. For any function f, as long as we have a one-dimensional function, okay, you just give me any one-dimensional function, sine, cosine, exponential, right? Even discontinuous. Well, let's forget about discontinuous for now. Give me any function f. You take the derivative with respect to time. What do you get? Use chain rule. Take one derivative, what do you get? What's the derivative of f of x minus at with respect to t? Yeah, minus a times f prime, right? Take a second derivative, right? Take derivative again for minus a times f prime. What do you get? You get another minus a coming out, right? So you get minus a squared, which is a squared, times f double prime, right? So that means d squared y dt squared is equal to a squared f double prime. How about the derivative to x? That's even easier, right? You take one derivative, there is no a, right? It's just f prime. Take another one, f double prime. So f double prime. Is this equal to a squared times this? Of course, right? That holds for any f. So that's one solution. Another solution that's equally simple is y of x t equal to some other function, x plus at. Do the same math, right? You take derivative of this y with respect to t, you get a times g prime. Take another derivative, you get another a times g double prime. So a squared times g double prime. Take the same derivative to x, you get g double prime. So this again is equal to that.